The question that we will discuss is IIT JEE 1992 question. In this question, there is a rod of given length, and on this rod, an insect of mass same as that of rod. It falls on this rod at a distance c, which is L by 4 from the center, and the velocity with which it falls is given as v. And after this insect, when it falls on this rod, it crawls along the direction b. There are two parts of this question. First part is we have to determine the angular velocity omega in terms of v and l, and the second part is we have to calculate the value of v when this insect reaches the end c. So the first part is in fact straightforward. It is based on conservation of angular momentum, and in second part I will do this question with two different methods. One is based on rate of change of angular momentum, and second one is on rotating frame reference. So this is our rod, and the insect is shown here with a blue color, and the insect will apply a force F shown by this line on the rod. Similarly, the rod will exert a force equal and opposite shown by this red line, and by Newton's third law, this force will be equal and opposite. Now there are two things which we have to consider here. One is that the linear momentum of the system will not be conserved, although it seems that these two forces F and F are equal and opposite, and if we consider rod and ball as a system, it seems that F and F is cancelling out. However, there is a reaction force which is developed here, that is, suppose it is Rx and Ry. So net force is not zero. There is a net force in x direction as well as in y direction, so we cannot say that the linear momentum is conserved. However, if we take, suppose this point is named as O, if we take the center of the rod, and now if we calculate angular momentum about this point O, then angular momentum of Rx and Ry will be 0, and angular momentum of F and minus F will also be 0. So net moment about this point O will be net angular momentum about this point O will be 0. So we can say that net torque about this point O will be 0. Sorry for this moment and torque, because they are used interchangeably in engineering. So by mistake I have mentioned moment. It is in fact torque. So net torque about point O is Rx is 0, Ry is 0, and for this F is R cross F, that will be 0, and for this R cross minus F, so they will all together sum to 0. So angular momentum of the system about point O is conserved. So initial angular momentum before collision, if the insect has initial velocity v before striking, so we can write it as mvl by 4, where mv is the linear momentum and l by 4 is the moment arm. After collision, we have to first find the moment of inertia of the system. So moment of inertia of rod is ml square by 12, and moment of inertia of insect is ml by 4 whole square. So total moment of inertia becomes ml square by 12 plus ml square by 16. And if after impact the system rotates with angular velocity omega, then this total moment of inertia into omega, this is the angular momentum after impact, and this value is the angular momentum before impact. This is your after impact. So when we equate these two, we will obtain omega equals to 12v by 7l. So this is the answer of the first part. This is our answer for the first part. Now moving to the second part. So before moving to the second part, let us consider ball and rod as a system. The forces that will be acting on the system will be, one is the mass of the insect, which is given as same as that of rod, that is mg. Contact forces will be internal forces, they will cancel out. That is the normal reaction, frictional force, etc. They will cancel out. So that is not shown here. And then the reaction forces, that is Rx and Ry, which are acting at the hinge point, and the weight of the rod. So total moment of inertia at any instant, suppose this rod is making an angle theta with the horizontal. So total moment of inertia will be the moment of inertia of the rod, that is ml square by 12, plus moment of inertia of the insect, that is mx square, where x is the distance from the center of the rod. So angular momentum of the system will be I into omega, where I is ml square by 12 plus mx square. Now if we take torque of the system, Rx, Ry and this capital Mg, these torque will be 0. The only torque that will be there will be Mg cos theta into x, that is the component of force perpendicular to the rod will exert a torque, and the moment arm will be x, so it is Mg cos theta into x. So now we know that torque is rate of change of angular momentum, so torque equals to dl by dt, and that equals to d by dt of I omega. If we substitute the value, and now in the question it is given that omega is constant, so when we take out omega from this differentiation, so omega comes out, and then we have d by dt of ml square by 12 plus mx square. Since ml square by 12 is constant, so its differentiation will be 0. This term d by dt of ml square by 12 will be 0, and other term will be mx square by 12. So this term is, in fact, when we will differentiate ml square by 12, it will become 0. By mistake it is written here as 0. So finally the equation becomes omega d by dt of mx square, that is omega m d by dt of x square. So finally after differentiation it is 2x omega m dx by dt. Now equating this with the torque, that is mg cos theta into x, we obtain the equation 2x omega m dx by dt equals to mg cos theta into x. Now substituting this value dx by dt as dx by d theta into d theta by dt, we obtain 2x omega m dx by d theta into d theta by dt, that equals to mg cos theta into x. So now cancelling out, x will cancel out here, x and x will cancel out, m and m will cancel out. So our final equation becomes dx by d theta by dt here is omega, so I have put the value as omega. So 2 omega square dx equals to g cos theta d theta. When the insect crawls from the midpoint, that is from the distance L by 4 to L by 2, the angle turned by rod is pi by 2. It is given in the question. So these are the limits that we have used here, that is L, and the distance moved by the insect, which is from L by 4 to L by 2, and this is the angle rotated by the rod, that is 0 to pi by 2. So after integration we obtain this 2 omega square L by 4 equals to g. So finally we have omega equals to 2g by L. Now earlier we have calculated omega. In the first part we have calculated omega as 12 v by 7L, and from the second part we have calculated omega equals to root 2 GL. So finally we obtain v equals to 7 by 12 root 2 GL. Substituting the numerical value, we finally obtain this value as v equals to 3.5 meter per second. This is the answer of our second part. Now I will do the same problem with a rotating frame reference. So moving to rotating frame reference, first I will consider the free body diagram of this insect. The forces acting on the insect are its weight mg, the normal reaction n, the frictional force whatever it may be f, and I have resolved the forces into mg cos theta and mg sin theta. Now using the polar coordinate, don't worry too much about this polar coordinate, it is also same little bit of extra from this Cartesian coordinate. The acceleration in radial direction is given as r double dot minus omega square r, and in theta direction it is given as theta double dot plus 2 omega r dot. So the forces in radial direction are this F, that is the frictional force, and mg sine theta. So we can write the equation F radial equals to mass into acceleration in radial direction. This is our Newton's law. Similarly, in theta direction we can write F theta equals to m into a theta. This is again Newton's second law. So substituting the value of radial forces, that is F minus net force in radial direction, F minus mg sine theta equals to r double dot minus omega square r. I have taken this towards center as positive. Similarly, in theta direction it is mg cos theta minus this normal reaction. This is our theta direction, the tangential one. Mg cos theta is in the direction of motion of this rod, and normal reaction is opposite to that direction, and that equals to, sorry for this should be equals to mass into acceleration, m ar and m a theta. Now we have to find out these unknown forces like F and N, and we have also to find out this r double dot. R double dot is in fact rate of change of position vector with respect to time. It is the second differentiation. It is r double dot is d2x by dt square, where x is the radial distance from the center of the rod. Similarly, r dot, this is r double dot, and r dot is dx by dt, r dot is dx by dt. So in order to find out these unknowns, we will first look the free body diagram of the rod. So this is the free body diagram of the rod. The forces acting on it are Rx, Ry, Mg, the normal reaction, and the frictional force. The moment of inertia of the rod, since it is hinged at its center, so it is ml square by 12. And the angular momentum of this system, in fact the system here is, we are talking about this rod. So angular momentum of the rod is I naught into omega, where I naught is moment of inertia, that is ml square by 12, and omega is the angular velocity. And in the question it was given that omega is constant. So in fact L is constant. So when we write torque equals to dl by dt, that is the rate of change of angular momentum, so d by dt of I naught into omega, and this term will be 0. And the torque that is acting on this rod about its center of mass is, when we are taking torque about this point, that is point O, Rx, Ry and Mg will be, torque of Rx, Ry and Mg will be 0. The dimension of thickness is assumed to be very small, so torque of this F will also be 0. So there will be only a torque of N, normal reaction, that is N. So in fact N into X equals to d by dt of I naught into omega, and this I naught into omega is constant, so N into X equals to 0. Now since X cannot be 0 because it is at a certain distance from the center of the rod, so N is 0. Now this gives a big doubt regarding this normal reaction, frictional force and all that. I will explain it one by one. This normal reaction equals to 0 doesn't mean we know that this will lead to the leaving to the contact of the surface, but this actually does not happen because there are other forces which constrain the insect to move in the given direction. And similarly, there is a doubt that if N is 0 then F will be 0. That is also not the case, because F equals to mu s into N, that happens in the limiting case, and it is not necessary that when N is 0 that this implies that F is 0. F may not be 0. Similarly, when N is 0, it doesn't imply that it will fly off. Of course it will leave the contact, but because of other forces it will be guided in its constrained path. So finally, when we obtain the equation in the theta direction, I have omitted the radial because that is not important for this question. So in theta direction we have mg cos theta minus n equals to m into a theta. A theta is theta double dot plus 2 omega r dot. Now n is 0, I have just explained, and this rod is rotating with constant angular velocity, so theta double dot will be 0. This theta double dot is 0 because rod is rotating with constant angular velocity, so rate of change of omega is 0. When we substitute this value n and theta double dot as 0, we obtain g cos theta equals to 2 omega r dot, which is same as the previous one where we have used derived this equation using net torque equals to rate of change of angular momentum, and here this we have obtained by using a rotating frame of reference. So 2 g cos theta equals to 2 omega dx by dt. Now after this it is exactly similar to what we have done earlier. We will rearrange dx by dt as dx by d theta into d theta by dt, and we will substitute the value of d theta by dt as omega, and finally we will put the limit, since the insect is moving from L by 4 to L by 2, so these limits are put here, and then we will obtain this expression 2 omega square L by 4 equals to g, that is omega square equals to 2g by L. When we substitute the value from the previous equation where we have obtained omega in terms of v, this equation, and finally substituting the numerical value, we obtain the same result, that is v equals to 3.5 meter per second. Thank you.